Okay, we're going to continue on here. So last time we got into electron configuration and how to write electron configuration. Again, a reminder, we do write electron configuration based on the order in which the electrons go into the atom. And again, you could really recreate the order by remembering what we talked about, that on the first energy level, that is only s orbitals available. Not until you get to the second energy level that you see p's, not until the third energy level, that's when d's start, and not to the fourth energy level, that is where f start. Again, you basically can just fill in the numbers after that. And this will give you the proper order as to how to fill electrons, writing electron configuration. Again, one of the major things that we talked about is the idea that those S there comes before the D's. So we do go 3P, then to the 4S, and then back to the 3D. And that pattern does follow all the way through. That in combination with what we talked about, s orbitals could hold a maximum of 2 electrons. If you fill up the entire p subshell, that's going to be 6 electrons. D subshell will be 10 electrons, and the F subshell will be 14 electrons. Again, because there's 7 different types of f orbitals, 5 different types of d orbitals, 3 different types of p orbitals, and only 1 different type of s orbitals. So when we talk about, again, a collection of orbitals on a certain energy level, like, say, the 2p orbitals, that is, again, sometimes referred to as a subshell or sublevel. It is all 3 of those orbitals together, where each individual one, again, can only hold basically 2 electrons maximum. So 2 times 3 gives you 6 total if you fill the entire thing up. So if we had something like, I know we were running through those last ones there. We were doing F, which was 9, I think. And again, we could do a 1s2, 2s2, 2p6, and 3s1. Once again, we could count up the top numbers here, and that'll tell us how many electrons that we put into each of these orbitals or subshells. And our total number there, which is 11, which is way too far as to where I went there. That would be great if we were doing sodium, which was probably in my head there. So let's just make it sodium. So actually it looks better that way. Sodium's got 11, so that would work better than fluorine. Fluorine, which has 9, obviously would lay up a little bit earlier than that. 1s2, 2s2, 2p5. That's fluorine. That's better. So we can write our electron configuration like so, as we talked about. That's the way you want to do it. It should be superscript there for the electrons. Remember, the first number is what's referred to as the principal quantum number. That is essentially a fancy word for the energy level. So in this particular one, we have 2 electrons on the first energy level. We have 8 electrons on the second. And on the third energy level, we have 1. Here we have 2 electrons on the first, 7 electrons there on the second energy level as well. Any questions on that stuff there we were talking about? So let's do one here. Let's just do, when we do our friend calcium, which is 20, why don't you write the electron configuration for calcium and see what you come up with. Okay, let's take a look. So remember, we always start up here at top. So we will row this way, and that will give us 1s2. We will zigzag back, come this way, gives us 2s2. Again, zigzag back, come this way, 2p6. If we count off the top numbers, we're at 10 electrons, so halfway there. We'll continue on. Next, again, is the 3s, and we can put 2 into there. Zigzagging back is going to be our 3p6. Again, if we count up the top numbers, that's 18. Next again is 4s comes next, as you can see in that order, and 4s2 in this particular case here. Any questions on that? Now, when we look at this configuration up through here is 18 electrons. And if we look on the periodic table, number 18 is our friend argon. And argon is a noble gas. So we can basically write argon and then 4s2 for the electron configuration. Thank you. And that basically, the little brackets there around argon indicates the electron configuration for argon. And then you just kind of continue on. It does have to be a noble gas, which is group 8 on the periodic table, where we have helium, neon, argon, all those on. So it's got to be one of those guys on the periodic table that comes right before whatever you're writing electron configuration for. You could kind of do a shorthand. So for example, here, if we look at sodium, through our first little part of sodium there, that is 10 electrons, which from the periodic table is neon. And 3s1 would be the shorthand for that as well. So that's sometimes referred to as a noble gas configuration, as we use a noble gas in parentheses there, or brackets, and then you can continue on from it. But it's always a noble gas that comes right before the element on the periodic table, not after, so the one before. So that's why in this particular case here, we would, if we wanted to, would have to back up to helium. Most people wouldn't do it, but it has to back up to helium to do that one, which would be the noble gas that would happen. Any questions on that there? Now, speaking of electron configuration, if we do have something that has a charge, so for example, we'll use our two examples there, our sodium, which is 1s2, 2s2, 2p6, 3s1, and we'll use our fluorine, which is 1s2, 2s2, 2p5. And if sodium, for example, had a +1 charge, what that means is sodium with no charge has 11 electrons. Sodium with a +1 charge actually has 10 electrons in this case. And that is because, again, sodium has 11 protons and only 10 electrons, which gives us a net +1 charge in this particular case. So when we write the electron configuration for something with a charge, and by the way, something with a positive charge like this guy is what is referred to as a cation, positive charge guy. And that is an ion. An ion in general is anything that has a charge associated with it. So the electron configuration for sodium with a +1 charge would be 1s2, 2s2, 2p6. That again is the same thing as neon's configuration, basically. Now, if we look at fluorine, fluorine typically will make a negative charge, and it typically will make a -1 charge. And fluorine with no charge, as we can see here, has 9 electrons. And fluorine with a -1 charge actually has 10 electrons. And that is because fluorine has 9 protons and will need 10 electrons to give us a -1 charge overall. 9 positive things, 10 negative things leaves you 1 negative thing left over, which is where the charge comes from. And we also need to adjust it. It would be 1s2, 2s2, 2p6, or it would also be neon's configuration. So all three of those things, sodium, fluoride, and neon, they all have the same electron configuration. They are all what are referred to as being isoelectronic with each other. Isoelectronic, again, means the same electron configuration. By the way, something that is negatively charged is what is referred to as an anion. So as we can see here, something with a positive charge has lost electrons, like I think we might have talked about when we were doing protons, electrons, atomic number. Something with a negative charge, which is an anion, again, has gained electrons. That's why they are negative. they have more electrons than protons, and that's why those guys that have lost electrons are positive, because they have more positive protons than electrons. So if you see a positive charge, it means it has lost an electron or two or three, or however many it is, from its neutral guy. And if you see a negative charge, it has gained electrons from its neutral self. So you do need to adjust electron configuration if you do come across anything with a charge. And what you actually see here is a very common thing that happens. Our representative elements basically end up at noble gas configuration. And that is because that's really the basis of all bonding, which we'll talk about in the next chapter. The basis of all bonding is for everybody to end up as the same electron configuration as a noble gas, because noble gases are very, very stable. So that's the goal of all bonding, both ionic bonding and covalent bonding. It is important to remember that, as we'll talk about, they don't become the noble gas element because they're still the same element, because they still have the same number of protons as they started with, but they have the same number of electrons. So they're the same in terms of electrons, but sodium with a +1 charge is still sodium because it still has 11 protons, which is what really makes it sodium to begin with. Any questions on electron configuration with charges? All right. So on the periodic table, there are different groups. And again, this is group 1, this is group 2, this is group 3, group 4, group 5, group 6, group 7, and group 8. And on the periodic table, the first two groups are the S block on the periodic table. Groups 3 through 8 is the P block. The transition metals, which are between these two groups, is the D block. And down on the bottom there, those two rows, is the F block on the periodic table. So S orbitals, right, can hold 2 electrons. So that's basically 1 and 2. P's could hold 6 in those subshells. 1, 2, 3, 4, 5, 6. D's could hold 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And you could trust me, if you count all those boxes, you got 14 boxes on the bottom, which would represent 1 electron into each of the F orbitals on the bottom. So if you know what you're doing, you could actually count off the electron configuration from the periodic table. But you do have to be careful along the way when you do that. So for example, we got something like hydrogen here, we got lithium there, and right about there is sodium. So if we were to do, say, sodium that we just did, starting right here at hydrogen, there are 7 periods as well. 1, 2, 3, 4, 5, 6, and 7 periods-ish. And we would go across 1s2 to helium. We would come this way, which would be 2s2. This would then be 2p6 to the end. And starting here would be 3s1. So you literally could kind of count the boxes as you go through it. You do have to be careful because, right about here, that is the 4th period, but that is the D right there. And D start at what level? You start on the 3rd level. So that's actually 3D there, even though it's on the 4th period. It's 1 behind the period number. And F's, which should be, in this area, actually over 1 in that area, are 4F and 5F. So I probably wouldn't recommend counting off the periodic table unless you really do know sort of what you're doing. There are places where you can go pretty bad, but it can be a good place or way to check yourself as you're doing electron configuration. But again, when you get to the transition metal region, it does get a little, kind of different. All right, so here's another example of that sort of shorthand. Speaking of the transition metal regions, there are a couple of exceptions in that transition metal region. And the 2 notable exceptions that you need to worry about is chromium and copper. Chromium is number 24 and copper is number 29. And if you were to sort of follow the zigzag approach there for chromium, you would end up with 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. And the exception actually happens here. There actually is one more electron up in the d orbital and one less electron in the s orbital. So the correct configuration, and by the way, if we shorthand this part of it, that is 18, which is argon. And it should be actually 4s1, 3d5. So that is an exception that you should be aware of. There's actually, again, one more electron up there in the d and one less. Copper is also a similar exception. It is argon 4s1, 3d10 rather than 4s2, 3d9 like you would get if you followed the zigzag approach there. The reason for that is they are super close in energy to begin with. So when we fill up the 4s first, and then we fill up the 4d or 3d, it's not a lot of energy needed to kind of promote that electron up there to the 3d. So it happens. It makes it a little bit more stable. And if you also look on the periodic table below chromium and below copper and kind of come in, you'll find a lot more exceptions actually in electron configuration. Things like silver is an exception. Things like PD is an exception. PD doesn't even have any electrons in the S. They've all been moved up to the D. So there's a lot more exceptions. But for us, these are the two main ones that you do need to know. And again, that would be the correct electron configuration for chromium. And that would be the correct electron configuration for copper. Any questions on that there? And again, the others, you could just know that they are there, but you don't have to worry about them for us in here. Any questions on that there? Speaking of transition metals and speaking of when they do, for example, lose electrons. Let's come back here, actually. Let's say we took something like iron, which is a transition metal, and it's number 26. If we write the electron configuration for iron, it'll be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. So if we fill in our electrons here, this is pretty much what it will look like if each of these arrows represent electrons. And what actually happens, which is kind of confusing for some people, but what actually happens when electrons go into the atom is they will go into the lower energy 4s first, and then they'll go into the higher energy 3d next. But what actually starts happening once you start putting electrons into the d orbitals is they actually switch in energy. And what ends up happening in the case of transition metals is the 4s actually ends up being higher in energy than the 3d, and that happens after you start filling some electrons into the d orbitals. That is also why sometimes you will see, if you're just Googling around, which you should never do probably, but if you're just Googling around, you might actually see people write electron configuration all like in order. Like you'll see it like all the 3s together, all the 4s together. And that is electron configuration really based on energy rather than the filling order of how electrons go into the atom. In this class, and pretty much every single chemistry class you ever take, you always write it the way we were learned, the way we just learned there, and which is the filling order, which you should put the electrons into the S first and then the D, just in that order. There's only one class I've ever taken where you write it the opposite way, and most classes you don't do it. So here we are going to write the electron configuration like we did here in that order, and that is the proper order based on filling order. But the consequence of this is actually when something like iron loses 2 electrons and becomes a positive 2 charge, it now will have only 24 electrons. And the reality is, because of this switch in energy that occurs, the electrons that get lost first, always with transition metal, is always those S's. So if we were to write the electron configuration for iron that has a +2 charge, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and actually 3d6. We actually will eliminate these two electrons here, as those are the first ones that would go. And that's unusual for transition metals. Other things that you write that are not transition metals in the middle part there of the periodic table, those guys will typically always lose electrons at the end. Whatever you write at the end is kind of where they would lose electrons from. But transition metals, because of the switch in energy, is a little bit different. That means that if we were to go to iron with a +3 charge, that would then have 23 electrons, which means it will again lose 3 electrons. So those 2 electrons will be lost. And at this point, it then has to go into the d orbital to lose 1 more electron. And we will end up with 1s2, 2s2, 2p6, 3s2, 3p6, 3d5. So transition metals are a little weird the way they lose electrons. In a sense, they will always lose the s electrons that come before them, because after we put the d electrons in there, they're actually highest in energy. And that's typically the electrons that atoms lose, or the highest energy level electrons are the ones that are basically lost in the process, really, of bonding, and when they make an ionic bond like that. Any questions on that there? Okay, any questions on electron configuration there? All right, so let's talk a little bit about valence electrons. So valence electrons are really the ones involved in bonding. They are the highest energy electrons found in an atom. And you can find the valence electrons by looking at the electron configuration, like we see here with nitrogen. We have 2 electrons on the first energy level, and we got 5 electrons here on the second energy level. Those are valence electrons. The lower energy level electrons are sometimes referred to as core electrons. They are not involved in bonding because they're frankly close to the nucleus and held tightly, so they're going nowhere. So it's really only the valence electrons that are definitely involved in bonding. If we looked at something like our sodium, which was 1s2, 2s2, 2p6, 3s1, right here is its 1 valence electron. So one way that you can figure out valence electrons is to simply write the electron configuration, but probably the easiest way to do it is you can figure out the number of valence electrons based on the group number on the periodic table. So if you look at a wonderfully drawn periodic table here, that's group 1, that's group 2, 3, 4, 5, 6, 7, and 8. Everybody in group 1 has 1 valence electron. Everybody in group 2 has 2. We're going to skip the middle part here. This is going to be group 3 has 3, 4, 5, 6, 7, and 8 valence electrons. So that is a much, much faster way to figure out valence electrons. The one exception over here in group 8 is our friend helium. And helium has only 2, and that is because it only has 2 total electrons, so it can't have 8. So everybody else there on the group 8 will have 8 valence electrons, but helium will only have 2, as it has only 2 to begin with. So we see fluorine is group 7, has 7 valence electrons. Chlorine is group 7, has 7. And carbon is group 4, which has 4. So much, much easier way of figuring out valence electrons. So let's talk a little bit about periodic table and some trends. As you go down a group, which is up and down on the periodic table, we start to see the reactivity of metals start to increase. So in order of losing electrons, cesium, rubidium, potassium, sodium, and lithium, this is basically going up group 1 on the periodic table. And those guys, more reactive as you go down. The most active nonmetal is found in the upper right of the periodic table. So when you look at the periodic table, pretty much up here where we have our nonmetals, upper right is the most reactive nonmetal. And down here is where we find our most reactive metal. And we're going to talk really why that is here based on some periodic trends as to why we do see those opposite locations as being most reactive. So the first sort of periodic trend we want to talk about is what is referred to as ionization energy. Ionization energy is the energy required to remove an electron from an atom in the gas phase. So when we talk about ionization energies, this is the energy required basically to make cations. So that is what happens when somebody loses an electron, they become positively charged. And the general trend in ionization energy is, as we'll see on the next slide, it increases on the periodic table as you go that way, and it decreases as you go left and down on the periodic table. Metals have relatively low ionization energy, which means it doesn't take a lot of convincing for them to lose their electrons. Non-metals have very high ionization energy, which means they're not very interested in losing electrons, basically. Electrons actually come off one at a time. They actually don't all pop off at once. So for example, if you took something like magnesium, the first thing that would happen is magnesium would lose one electron, become positively charged. That's what's sometimes referred to as the first ionization energy. The next thing that would happen is magnesium would +1 charge, would lose another electron, become a +2 charge. That is what is referred to as the second ionization energy. Then what would happen is magnesium with a +2 charge would lose one more electron and become a +3 charge, which is the third ionization energy. Now, is it easier, you think, to remove the first electron or the last electron? Which one's easier to remove? It's actually the first electron is actually the easiest to remove. It is neutral at that point. So when you remove the first electron, does the ion become larger or smaller? If it loses electrons, electron cloud gets smaller, shrinks, right? So it brings in all those other electrons now closer to the nucleus, which is positively charged. It's going to hold them tighter, which means when you pop off the next electron, gets smaller again, right? Which means those electrons are now even tighter and closer to the nucleus and held tighter. So it's actually much easier to take off the first one versus the second versus the third. And that's what we see as you go from, say, first ionization energy to second to third, we see an increase in the ionization energy between each electron that pops off. And we also know, for example, if we look at the electron configuration for magnesium, which is 1s2, 2s2, 2p6, 3s2, magnesium has how many valence electrons? Has 2, right? And we know that also because it's group number 2, which is there. So when it loses this first electron and becomes +2, that's okay. That's right there, a valence electron. When it loses the second electron and becomes +2, that's okay because that's a valence electron, which means after I lose those electrons, which electrons are left here after my valence electrons? Those are my core electrons, which are much closer to the nucleus, even closer now that we lost all those electrons. Good luck trying to do that. And that's why something like magnesium definitely doesn't do that. It's probably about a 10-fold increase in the amount of energy that would be required to try to rip that off, and it will not happen under normal conditions. And that's why certain things will only form certain charges, like magnesium will only form a +2 charge because it's easier to get rid of those valence electrons, but much, much tougher energy-wise and not really energy favored to get rid of those core electrons. So same thing with sodium. If we look at sodium, electron configuration, 1s2, 2s2, 2p6, 3s1. In this case, that was my, there goes 2p, 3s2. So that is sodium, which is 11 right next door. When it loses one electron, it is now into its core electrons. And again, it's going to be much, much harder to try to do that energy-wise. It's just not going to happen. So this is one of the reasons why certain things only form, certain types of charges because it's just too hard to try to rip off those electrons really close to the nucleus at that point. By the way, when somebody gains an electron, does the ion become larger or smaller? it becomes larger, right? So it gains electrons, electron cloud gets bigger. So the guy with a negative charge will start to grow in size as it gains all those electrons to its sort of electron cloud. So the general trend in ionization energy, again, increases as you go up to the right, decreases as you go down to the left. That relates to a couple of other important sort of trends that we'll talk about here. There is electron affinity. And that's the energy change when an electron gains, when an atom gains an electron. And on the periodic table, it increases as you go this way, and it decreases as you go this way. Another really sort of important trend that sort of falls with all these guys is something that sounds very similar, but it's a little bit different, is what's known as electronegativity. And electronegativity is the ability of an atom to bring electrons towards itself. And it also increases as you go up and to the right on the periodic table and decreases as you go down. Fluorine is the most electronegative element you can have. Fluorine is as far over up and to the right as you could get, other than noble gases, which again are very happy the way they are. They're not looking really to gain or lose electrons. So these two trends, along with ionization energy, along with atomic size, which is the last sort of periodic trend, they all fit together with basically what we see when we look at metals and non-metals, and really what happens with each of these guys when they are interacting with one another and try to come into bonding contact with one another. So if we look at our atomic size, as we go up and to the right, it gets much smaller. And if we go down and to the left, the size of the atom gets much larger. Down to the left, we have a lot more electrons, which means they're higher energy levels. They're further away from the nucleus, so we're going to make it much, much larger. As we go to the right, we get kind of a bigger positive nucleus charge there going to the right, and that's going to bring even those outer electrons in closer because the strength of that positive charge is stronger to bring those outer electrons in, and we get a much smaller size. So if we steal this chart here, we have the size gets smaller as you go to the right. We have our ionization energy increasing as you go that way and decreasing as you come this way. We have our electron affinity increasing as you go that way, decreasing as you go that way. And we have our electronegativity increasing as you go this way and decreasing as you go down. So basically, when we think about what we said earlier, that our nonmetals are up here in the upper right of the periodic table, we have things that are very small on that side of the periodic table. We have things with very high ionization energy, which means good luck trying to take an electron from them. They also have very high electron affinity, which means they like to gain electrons. And they have very high electronegativity, which means they like to hang on to their electrons and they want to take somebody else's electrons. So all of those sort of trends is why we see nonmetals typically gain electrons. So our nonmetals here typically will gain electrons, become negatively charged, or anions. When we go to the other side of the periodic table, left and down, we have atoms that are larger, which means their electrons are not held as tightly, so they have very low ionization energy, which means it takes not a lot of convincing for them to give away their electrons. They have really low electron affinity and electronegativity, which means they're not interested in gaining electrons or taking anybody's electrons. They're pretty much interested in take my electrons, please. And that is why when we see metals, they typically will lose electrons and become positively charged and become what are known as cations. And that's why when we make something like an ionic compound, which is a metal and a non-metal, it works really well together because the metal is like, take my electrons. Non-metal is like, thank you, I was looking for some electrons. And that is why they kind of work really well together. And we get a transfer of electrons from the metal to the non-metal. Any questions on that? And it's really because of these sort of periodic trends here that we see. Any questions? So that brings us into a little prelude here to bonding in the next chapter. But Lewis dot symbols is also sometimes referred to as electron dot symbols, just generically called electron dot symbols. And these are symbols that we use the chemical symbol and basically one dot to represent each of the valence electrons there are. There really is no big rule, except that usually you don't put more than 2 dots per side. And since there's 4 sides to each of the symbols, that's a maximum of how many dots? 8, and 8 valence electrons on the periodic table is our noble gases. And as we'll talk about much here, that is the purpose of all bonding, again, is for everybody to achieve that noble gas configuration in terms of their electrons and be just like those noble gas configuration. So here's an example of that. And again, if you have something like sodium, you would just put 1 dot. You have something like calcium, you would have a couple of dots. A lot of times people kind of do 1 at a time and then kind of roll through and pair them up. But again, as long as you don't do more than 2 per side, it's okay. So here is everybody. Group 1 has 1 valence electron. Group 2 has 2 valence electrons, 3, 4, 5, 6, 7, and 8. There's our helium, which has only 2 electrons. And as we'll talk about with bonding, the goal is to get to noble gas configuration. So pretty much everybody wants to get to 8, except for one element, which is the element that comes before helium. Yeah, hydrogen just needs to get to helium. So hydrogen should only need 2 electrons, should never, ever, it's good to repeat this, ever have more than 2 electrons. Yes. So pretty much hydrogen should always look like this, basically. One line which represents 2 electrons or something like this. You should never find yourself triple bonding hydrogen and putting dots because you're going to get a bigger X happening on it. Yeah, so don't do it. People go crazy with hydrogen, put stuff all over it. So hydrogen just needs 2 electrons to get there. Everybody else needs that magical 8 number to be like the noble gases. And they will, as we'll talk about with bonding, continue to make bonds until pretty much they get there. Any questions on that there? That is chapter 4 there. All right, we're going to go off to chapter. Okay, we're going to do here chapter 6, a reminder that we are skipping chapter 5, which is nuclear chemistry. So we're not going to do that chapter. So off to 6 here, which involves chemical bonding and also nomenclature. So we're going to talk about the bonding and the naming part here. Hang on a sec here. I'm sorry. I think I got the wrong one queued up here. I apologize. That's not going to work, is it? Or do I have the right one? I do have the right one, actually. No, I do. All right, perfect. Try that again. Take 2. We'll cut that out of the editing later. All right, so let's talk about chapter 6 here. The first thing we're going to talk about is nomenclature. We're going to talk about how to name everything. And there are certain rules in terms of naming, but there are a few things that actually do go by common names, and you should just use the common names when you come across these. I would say probably really the first 3 are probably the ones that are used mostly common names. Maybe not so much these guys, but definitely the first one is H2O. It is not a trick question. That is water. Yes, that is not dihydrogen monoxide. Nobody wants a refreshing glass of dihydrogen monoxide. I can't imagine why they don't use that name. So you don't want that. So just put water, move on with your life. It'll be okay. When you see NH3, that is ammonia. CH4 is the simplest organic molecule that you could have, and it is methane. It's the stuff that comes out when you light your Bunsen burner there in lab. I will say most people call NaCl sodium chloride, but it is sometimes referred to as table salt, and sucrose or table sugar there for the other one. But I would say definitely those first three, water, ammonia, and methane, you should definitely go by common name. So let's talk a little bit about sort of the process to name these guys. And there's really kind of two types of bonding that sort of crosses over into naming. And when we name binary compounds, which basically means they are two elements, there are ones that contain a metal and a non-metal. And whenever we have a metal and a non-metal together, that is always going to result in an ionic bond. And as we just talked about, based on our periodic trends, the metal will always be the one that will transfer electrons to the non-metal. And the result of that is our metal will form an ion, which is a positively charged ion. Our non-metal will form an ion, which is a negatively charged metal. And it is that attraction, which sometimes referred to as the electrostatic attraction, opposites attract, that hold that together. There's absolutely no sharing of electrons in an ionic bond. So that's a really important distinction. In an ionic bond, you have that positive charge and negative charge is what's really holding those ions together. No sharing of electron happening. And that's different than when we get two nonmetals together. When we get two nonmetals together, that's going to result in what is referred to as a covalent bond. And a covalent bond is always between two nonmetals. And there's some aspect of sharing of electrons. And the reason for that is what we were just talking about, the periodic trends. When you look at the periodic table, metals over here, non-metals over here. So when a metal and a non-metal get together, they have very different themes in terms of what they want to do with their electrons. Again, metals don't really want to hang on to their electrons. Non-metals want to gain electrons. So that is why we get a transfer of electron that happens when we have an ionic bond. When two nonmetals get together, they are both hanging out in the exact same location or pretty close location on the periodic table, which means they both really want to hold on to their electrons and gain electrons. So what happens when two nonmetals get together is the best that they could agree upon is we'll share electrons. There's some aspect of sharing that will happen because neither one of them will give away their electrons very easily like a metal will do. And that's where we get the sharing of electrons that happen. And as we'll talk about, the sharing could be equal sharing or it could be unequal sharing. And that results in what is referred to as a nonpolar bond when it's equal, or a polar bond when it is unequal sharing of electrons. But in a covalent bond with two nonmetals, there's some aspect of sharing of electrons that is happening. Questions on that? Now, depending on what type of compound it is very different in terms of how we name them. So it's important sometimes to first, even with naming, identify what you're dealing with in terms of the type of compound, and that will help you go down the right path, hopefully, for naming. So let's start with type 1 and type 2 compounds on the periodic table. Type 1 and type 2 are both metals and nonmetals. These are both ionic compounds, or ionic bonds. And when we have a cation and an anion, the cation is always written first. And let's talk a little bit about the periodic table and some common charges that we see on the periodic table. So everybody in group 1 will form a +1 charge. Everybody in group 2 will form a +2 charge. Remember, we skipped the middle part, which is our transition metal region. We go to group 3, 4, 5, 6, 7, and 8. Everybody in group 3, which is really aluminum here, will be +3, and it's really the only one probably from group 3 that you deal with. Remember, there's that staircase that kind of comes down right about there. And the nonmetals, which are again above the staircase, there's no real good pattern for 4, but starting in group 5, the nonmetals above the staircase are -3. The nonmetals above the staircase, -2 in group 6, and -1 there in group 7 in that case. So it kind of goes +1, +2, +3, skip, -3, -2, -1. No charge for group 8 because, again, they are noble gases, so they ain't looking to do much. Now, transition metals can have a varied positive charge. And that means something like copper could be +1 or +2, depending on the situation. Iron could be +3, +2, depending on the situation. There are 3 exceptions in the transitional metal region that actually has a fixed charges. And that is our friend zinc, which is, somewhere in this ballpark, and cadmium. Those guys are transition metals, but when they do form a charge, they will always form a +2. And if you hang a left-hand turn there at cadmium, you will find silver, and silver will always be +1. So those 3 transition metals, kind of like a backwards L going that way, although they are in the transition metal region, they really will have a fixed positive charge. Everybody else in the transition metal region, through here, here. And by the way, underneath the staircase over in this region, where we got things like lead and tin and antimony, those are actually metals on that bottom of the staircase, and those will be positively charged and also have a variety of charges, like lead could be +2, +4, tin, same thing. So they are not technically transition metals, but there's a few in this sort of area like lead or tin or antimony or bismuth that we do kind of come across, and they also can have, again, a variety of positive charge depending on the situation. So whenever we put a positive ion and a negative ion together, the overall charge has to be 0. So for example, if we were to take a calcium and a bromide ion, calcium group 2 should have a +2 charge. Bromide is group 7, has a -1 charge. When we put them together, we need an overall charge of 0. So in this case, you would actually need more of the Br minus. That gives you a grand total of -2 to balance out the +2 charge. And the correct formula here would be CaBr2 would be the correct formula there. When we write ions by themselves, like I did here, they should have charges. When we put ions together to make an ionic compound, they should never have charges. They should equal 0, even though they are made up of things that do have charges. So when we put a metal and a non-metal together, or a cation and an anion together, you need to do it in the simplest way that will get you 0 in terms of the overall charge. And again, when you write the formula, they should never have a charge when they are put together. But if they are individual, they should have the charges written. Any questions on that? Yeah. That's it. Oh, all right. Let's take a look here. Maybe I'll just do it here. So we have calcium is +2. We have Br minus, and again, we want to put it together so that we end up with no overall charge. So that's a -2. That is a +2. So +2 -2 gives us 0, which gives us our calcium and Br2. So again, always want the smallest or simplest way to get it to 0. So for example, if I had something like potassium here and oxygen, when I put that together, what do I need more of to get it to 0? Potassium in a grand total of 2. We could actually just write them next to it. It makes it easier. That's a +2 to go with our -2. That means I go K2O would be my proper way of writing that. That is the positive guy first, followed by the negative guy second, metal, and then non-metal. Number of how many we have goes here. We write nothing if it's just one, and it always goes to the number to the left. Yeah. Yes. Because that's exactly what we needed to get to zero, right? There's how many total of these guys? Calciums? There's just one. And there's how many of these Br minuses? Two. And that's what the two represents. The number goes always to the guy to the left. So with nothing written next to the Ca, that means there's one of those ions that have a +2 charge. And with the two there, it does not mean it's Br2 minus or something like that. It's two individual Br minuses, just like I wrote it up on top. And that's what that represents. Yeah. And this would be the cation. And this would be the anions here. Other questions? And again, that's why over here, 1 and 2 potassium. So that's what the 2 is there for. We have just one of those ions. And again, we don't typically write one here in chemistry. Other questions? All right, so let's talk a little bit about type 1 and type 2 compounds here and sort of the difference. Since I scribbled on this page, I'm going to get rid of that. So the difference between type 1 and type 2 compounds is always the metal. And whenever you have a metal and a non-metal together, which is what each of these are, that is always the most important thing. So the metal is always the one that will determine how you should properly name these things. And when we have a type 1 compound, that's going to be guys from basically group 1, 2, 3, silver, zinc, or cadmium. They all have fixed positive charges. Now, type 2 compounds are going to be ones where the metal has a varied positive charge. And those are typically going to be our metals that come from the transition metals, are just to the right, underneath that staircase. So again, it's going to be our transition metals and some of those metals down here underneath the staircase will fall into these type 2. So as I mentioned before, something like chromium could be +2 or +3, which is a transition metal. And something like copper can be +1 or +2 in this particular case. So when we go to name these guys, it is different depending on which one you're dealing with, either a type 1 or type 2. So the first thing you want to identify is it a ionic compound? And secondly, you want to identify pretty much where the metal is on the periodic table, and that's going to direct you into how you should go about naming these guys. Any questions on that so far? So how do we go about naming just positive ions, or which are cations by themselves, or anions by themselves? Well, positive cations are pretty easy to name. We just use the whole name. So as we can see here, that is Na+, which is the sodium ion. That is Li+, which is the lithium ion. That is K+, which is the potassium ion. Ca2+ is the calcium ion. So if I have any of those guys there that are positively charged, you basically just use the whole name of the element and you put ion at the end. So if we have something like H+, that would be the hydrogen ion. Now, things that are negatively charged, which are anions, we use the root of the name and we drop the last part and we put IDE at the end of it. So N is nitrogen, drop the last part, it becomes a nitride, IDE ion. P is phosphorus, drop the last part, it becomes phosphide, IDE. Oxygen, we drop a lot of the name and put IDE at the end of it, which becomes oxide ion. And hydrogen is the only element that can go both ways. It could actually be negatively charged as well in certain cases. And we would follow the same pattern. It would be the hydride, IDE, ion. So if you have an ion by itself, you should write the formula that includes the charges, and you should name it as either the whole name of the element or IDE there on the negative side. Any questions on that there? So let's get into some of this here. Let's talk about the rules for type 1. So type 1, we always go, as I said, the cation first, followed by the anion. So always the positive first, followed by the negative. That goes for both the formula and also the name. So that is always how it goes. Positive first, negative, both formula and name goes that way. And if we have type 1, it's pretty simple. For type 1, it's going to have that group 1, 2, 3, silver, cadmium, or zinc. We simply use the whole name of the metal, and the non-metal gets the IDE at the end of it. So as soon as you recognize it as a metal and a non-metal, and as soon as you recognize it as the metal being a type 1 compound, you simply just roll the whole name and the non-metal name. So for example, we had this guy a second ago, that is CaBr2. Ca is calcium, which is a metal. Br is bromine, which is a non-metal. I am interested in the metal here, which is calcium. Calcium, again, is group number 2, which means it has a fixed positive charge no matter what the situation is. That is all I need. This guy should be called calcium and bromide, IDE. The 2 here has absolutely positively no effect on the name. Don't use a prefix. It doesn't make it more chemistry-like. It makes it more wrong. Yeah, so do not use a prefix in this situation. People want to use like dibromide because it seems more chemistry-like. It's incorrect in this case. The 2 is there for what we just talked about earlier, right? The 2 is there because there is actually 2 of these ions, right, that are present, and there is 1 calcium that is present. So again, that is why the 2 is there. It has absolutely no effect on the actual name. That is also why when we look at something like NaCl, Na is a metal, Cl is a non-metal, which we know it's ionic. The metal is the most important thing. So when I look on the periodic table, I see sodium in group number 1. I know it's a type 1 compound. Just need to use the whole name of the metal, which is sodium, and the chlorine becomes chloride. Yeah. Questions on that there? All right. So a reminder that although when we do put these ions together in an ionic compound and formula, metal and non-metal, we do want the charge to always equal 0. Once again, you want to do that in the simplest way possible. It does represent 2 things that do have charges. So if we look at this one, which is Ki, this is potassium iodide, and that is because, again, potassium is group number 1, has a fixed charge, so we'll use potassium, and iodine gets the IDE at the end of it. This is actually, it's actually 2 things that have charges. It is a potassium, which is the cation, and it is the I minus, which is group 7, is the anion. That is why we only needed 1 of each of them to make it work. Yes, +1 -1 gives me 0 when I add that together. So that is why the correct formula is just K and I together. Don't overcomplicate it. Yes, so just very simple, get to 0. Simplest way to do that. Any questions on that? All right, so why don't you try some here? Let me change some since I clearly did that one earlier. So let's just make this one. Let's make this one here. Why don't we also do some names to formulas? So what is the correct formula for? Let's do lithium oxide. Lithium N. Let's do aluminum sulfide. And let's try sodium nitride. All right, so on the left-hand side, give the proper name. Right-hand side, give the proper formula. Okay, let's take a look, see how you're doing. So we'll start on the left there to give some names. So we got some formulas. Remember, best thing to do is identify what you're dealing with. So we do see K, which is a metal, and Cl, which is a non-metal. So again, I know it's an ionic compound. And again, always a metal involved. That's where you should look. So we're going to look at the metal, which is potassium, and that's group 1, which means it has a fixed positive charge, and it's a type 1 compound. And frankly, that's all I need to know at that point. I'm just going to use the whole name there of the metal, which is potassium. Again, our non-metal is going to take the IDE ending and would be potassium chloride. This is made up of a potassium ion and a chloride ion, one of each. Again, +1 and -1, where the potassium ion there would be our cation and the Cl- would be our anion. Any questions on that one there? Looking at the next one, magnesium metal, non-metal. Once again here, metal takes the precedent, and magnesium's group number 2, which also tells me it is a fixed type 1 charge. Again, that is all I need at that point. I'm going to use the whole name of my metal, magnesium. And again, it's going to be chloride here. The 2 here has no effect on the name. Doesn't matter if we got 40 of them there, it will not have an effect. The 2 again is there because magnesium is group number 2, which means it has a +2 charge. Cl is group 7, which means it is actually Cl-, not like Cl2- or anything like that. It's actually Cl- is the correct ion. And we need 2 of them there to balance out that +2 charge. So that is what the 2 represents. Any questions on that one there? This is barium, which is a metal, hydrogen, which is actually a non-metal, right? So in this case, the barium is group number 2, which is a type 1 because it has a fixed charge. And we will start with barium. And this is actually going to be the negative version of hydrogen, which is hydride in this case. And again, the 2 here has no effect. This is because barium is +2. Each of the hydrides here is -1, so we need 2 of them. So again, that is what the 2 is for in this particular case. That is the only time hydrogen will be a negative charge is when it comes after a metal in an ionic compound like this. So pretty much all other times hydrogen is going to be positive, but in this case, it will only be negative when it comes after a metal. Any questions on any of those names there? All right, now we have names and we want formulas. So we still want to identify sort of what we're dealing with. So lithium is a metal, oxide is oxygen, which is a non-metal. So again, that tells you ionic compound, which means you have 2 ions. You have a positive cation and a negative anion. And when we put them together, our basic principle is 0 charge, right? So let's start with lithium, which is group 1, and that is Li plus because it is group 1. Oxide is oxygen, which is group number 6 on the periodic table. And those nonmetals in group number 6 is -2. Once again, I just want to get to 0. Do I need more of the positive guy or negative guy to do that? Positive guy. I actually need one more. Yeah, so you could just draw it like that if it helps. That means I have a +2 on the left, -2 on the right. That is 0. And now all you have to do is write what you drew. I have 1 and 2 of those lithiums, so Li2. And I have 1 of those oxygens. There we go. Yes, just like so. Any questions on that one? Same thing here. Aluminum is a metal. Sulfide is sulfur on the periodic table, which is S, is a non-metal. So we want to think about the basic ions that these things are, not, put them together yet, just the basic 2 ions. So aluminum being group 3 has a +3 charge. Sulfide, being group number 6, has a -2 charge. When I put 3 and 2 together, the simplest way to get to 0 is what number? The easiest way to know that is just multiply those two numbers together. We get when we take 3 times 2 is 6. Yeah, so 6 will get us to 0 as simple as possible. To get aluminum to 6, I need one more, right? And to get the sulfide to 6, I need 3 more, right? So that's a -6. That's a +6. Once again, you can just count up what you drew. I got 1 and 2. So that's an aluminum with a 2. I have 1, 2, and 3. That's an S3. Yeah. Question on that. Now, sometimes people are taught to do something like this, like move the charge down and up and stuff like that. And it works like 90 some odd percent of the time. So if you're good with 90% of the time, you can just blindly do that. Won't work 100% of the time. So sometimes it's best just to think about like we're doing here, just to balance it out to 0. You always get the right formula. If you just blindly move things diagonally, yeah, you'll blindly get some wrong answers at some point along the way. But most of the time it will work, but not 100% of the time. So I would recommend just kind of doing it like this. And like I said, if it helps you, just draw out everything. Yeah. Yeah, so if you're not sure what the common number to get to 0 is, probably the easiest way to do it is just take the two numbers and multiply them together. And that usually in most cases will give you the simplest way to get it to 0, basically. Yeah. So even if we did the top one here, we took 1 times 2 is 2, right? So we want to get to 2 basically in the top one. So it will work in most cases if you want to do that. Yeah. Other questions? So sodium is a metal. Nitride is a non-metal, which is nitrogen. So again, the basic units of these guys, sodium is group 1, which is a +1. It's our cation. Nitride is nitrogen, which is group 5, which is a -3. So once again, in this case, to get to 0, I need more of the positive guy, right? And if we multiply those numbers, that is 3. So I really need to get this guy to 3, which means I will need 1, 2, 3 of them. So that will give me Na3, and I still only have one of those guys. So that will give me my proper formula there. Any questions on any of those? You do need to be able to go obviously both ways. Yes. So name to formula, formula to name. Again, when metal involved, always the important thing to look at. Other questions? All right. So again, don't add extra things that shouldn't be there to make it fancier. So let's talk about type 2 compounds. And type 2 compounds are ionic compounds. They are also a metal and a non-metal together. So once again, we have that combination where we're going to get a transfer of electrons. But again, it is that metal that is the most important. And this is going to be our metal that's in the transition metal region of the periodic table. Are just to the right, as we were talking about. Again, you can kind of see it on this periodic table. Below the staircase, kind of where we have the Pb, the bismuth, the tin, those guys, although they are not transition metals, do fall sort of the same way in terms of naming as we do with transition metals. Obviously, the 3 other exceptions being zinc, cadmium, and silver is fixed positive charges, which is type 1. Now, the difference here is we could have multiple positive charges on the metal. So we have to do an additional thing when we go to name this, but it's pretty much named the same way as we just did. So you'll use still the whole name of the metal. You will still give the non-metal the IDE sort of ending. The additional thing that we use is actually a Roman numeral. And we use a Roman numeral to indicate the charge on the metal. So this is the positive charge on one of the metals. Very commonly confused as being how many metals we have. So it's not how many you have, it's if you took that cation positive metal out, what the actual positive charge is. So for example, we have the one that we see here. This is FeCl2. Once again, we could use our sort of identification here. That is a metal. That is a non-metal, which tells us it's ionic. We focus in on the metal, which is a transition metal, which tells us it's type 2. And it also tells us that we do have to figure out what the charge is on the metal. The good news is in type 2 compounds, you will always know the charge on the negative guy. So you'll always know the charge on the negative guy, and you can kind of work your way backwards to figure it out. So in this particular situation, I do know that iron could be a couple of different charges. But the one thing I do know for sure is when I look at Cl on the periodic table, that is group number 7, which means it should have what type of charge in group 7? Should be a -1. And there's not just one of them there, but there is 2 of them, which gives me a grand total of -2 happening there for the Cl. Now remember, we need to get it to 0, and we only have 1 iron, which means the iron in this case has to have a charge of +2 to balance it out. And that's the additional thing that you have to do in this. And we also have to do the additional part of the naming. We still use the whole name of the metal, which is iron. This would be Roman numeral 2 for the actual positive charge that's on the iron. And once again, just like last time, regardless of how many of these negative guys we have, has no effect on the name. It is still going to be here chloride. Once again, no dye, no prefixes, none of those things. This is going to be iron Roman numeral 2 chloride. Question on that. Now, why do we have to use the Roman numeral? Well, we have to use the Roman numeral because it can be something else. For example, if I had FeCl3 in this case, I still have my iron, which I'm not sure what the charge is. But now on the Cl side, I have 1, 2, and 3, which means in this particular case, the iron has what type of charge? +3 charge. So we need to say in this one, this is iron Roman numeral 3 chloride. So we want to tell people basically when we're naming things that in the first case, we're dealing with the iron that has a +2 charge. In the second case, we're dealing with the iron that has a +3 charge. We do not need Roman numerals on type 1 compounds because they have fixed charges. So no matter what you do to sodium, it's always going to be +1. It doesn't matter who they hook up with, it will always be +1. So there's no need to tell somebody that's +1 because it cannot be anything other than basically +1. Any questions on that there? All right, so why don't you try this? What is the name of this guy here? Pb is lead, by the way. And it's just to the right of the transition metals, but it is named the same way. So see what you come up with here. Look, so Pb is lead. O is oxygen. So that's a metal, non-metal. Once again, it is the metal that's most important. We will find this metal actually again underneath the staircase to the right of the transition metal, but it is in that region that is named the same way as a transition metal. They can have multiple charges. So in this particular case, we have a lead with, I'm not sure, but we do have oxygen, which is group number 6, and that means it should have a -2 charge. And once again, here there are 2 of them, which means that's a -2. It's a grand total of -4, which means in this case, the lead is +4. So this would be lead Roman numeral 4. And once again, oxide would be there. This would definitely be a case where if you did the switcheroo, you would get the wrong number. Yes, because you would bring the 2 up there and the 1 there and be wrong. Yes. So again, it does not always work in all cases, just randomly switching the numbers back and forth. Any questions on that one there? All right. Now, we're not going to really use this, but there is sort of an older way of naming guys that have variable charges. We will strictly use Roman numerals, but the one with the higher charge sometimes ends with ic, and the one with the lower charge, positive charge, ends with ous. So, for example, ferric and ferrate, ferrous are very commonly still used sometimes today, and cupric and cuprous is also used for copper. But we will not use that. We will strictly use the Roman numerals if it is a type 2 compound, like we see here. So again, these are some of the type 2 metals that you'll come across. The interesting one is actually mercury here. This is Hg22 plus and Hg2 plus. This is actually mercury Roman numeral 1, the one that has all the 2s. The one that has only 1 2 is actually mercury number 2 there. So that's an unusual one right here. The way you could tell the difference is usually the 2 will still hang around, and that's because it's really mercury 1 is 2 mercury 1s together. So that's why there's a 2 on the bottom, basically. But for an example, if you had something like this versus something like this, this is mercury 1 oxide because the 2 is still there. This one is mercury 2 oxide, no 2 there. So that 2 will oftentimes kind of hang around still on the bottom when it is mercury 1 versus mercury 2. And but other than that, the other ones are not too bad, but mercury is kind of like a weird one in that sense. So just remember, for mercury, the one with the more 2s is actually mercury 1, and the one with the least number of 2s is actually mercury 2. It's an odd sort of way it is together. So as we talked about the rules for naming our type 2 compounds, pretty much the same thing as we did for type 1. Again, we do have to add the addition of the Roman numeral for the actual charge that we see on the individual metals. Bless you. All right, so why don't you try some here, and we'll give you some maybe to do some formulas. Let's do copper. To nitride. Okay, let's see how you're doing. So we'll take the same approach. I see CO, which is cobalt, that's a metal. Cl is chlorine, which is a non-metal. So again, always the metal is important. Cobalt can be found kind of in the middle there, the transition metal region on the periodic table. That should automatically tell you it's a type 2 compound. So we kind of need to figure out what cobalt's charge is here. We can again look to what it's attached to, which is Cl, which is group 7, which means it has a -1 charge. And there are 3 of them. So that's going to give us a -3 charge for the chloride side. That means again here to balance it out, that's going to be a +3 charge happening there for our cobalt. Once again, we're going to use the whole name of cobalt. We're going to insert the Roman numeral of 3 because of the charge. And again here, regardless of how many we got going on there, it's just going to be chloride at the end of it. Any questions on that one there? CuI, Cu is copper. Said it right, there we go. That's a metal. I is iodine, which is a non-metal. Our copper also in the middle there, the transition metal region, number 29. So that implies that it has a variable charge. Here, I is also group 7, which has a -1 charge. Since we only have one of them in this case, that means to balance it out, our copper has to carry a +1 charge to get to 0. We will use the whole name of copper. We will use Roman numeral 1 again for the positive charge that's on the copper, and our iodide, IDE. We'll drop the last part there of iodide. 9, IE, INE. Any questions on that one there? Lastly here, we got tin, which is a metal. We have Br, which is a non-metal. Tin is one of those, again, underneath the staircase that is not a transition metal, but can have a variety of charges, so it's named the same way. That means we also need to figure out what the charge is. In this case, we do know that Br is group number 7, and that's a -1 charge. And again, there's a 4 there, which means it's got a -4 charge. And since we only have one tin present, that's got to be a +4 charge to balance it out. That gives me 1 tin and 1, 2, 3, 4 of those guys, which is how we get to that formula. But this would be 10 Roman numeral 4 because of the charge. And again, regardless of how many we got going on there, it is just going to be bromide at the end of it. Any questions on any of those names? All right, now going from names to formulas, we again just want the basic ions in this case, if they are ionic. And in this case, they are. We see copper, which is a metal. We see nitride, which is a non-metal. The nice thing about this is I see a Roman numeral, which tells me that the copper has what type of charge? +2. That's exactly what the Roman numeral tells you. You don't have to figure it out. It actually tells you. Nitride is nitrogen from the periodic table, which is group 5, has a -3 charge. So common number between those two that will get us to 0 is 6 in this case again. So all we have to do is just build 6 on both sides. So I got 2 over here, so I need 2 more and 2 more. So that gives me the 6. And I need 6 over here, which means I just need 1 more of those ions. Once again, that is 1, 2, 3 coppers. And that is 1 and 2 of those guys. Yeah, there we go. Yeah. Any questions on that one? Lead 2, again, lead with a Roman numeral 2 means we have a lead with a +2 charge. Bromide is group 7, which means it has a -1 charge. So again, to get to 0, we need more of the Br minus, really to get to 2 in this case. So we just need to get this guy to 2. And once again, we can just write what we have. So we have 1 of those, and we have 1 and 2 of those. Gives us our formula in this case, yeah? Any questions? Lastly, iron Roman numeral 3. Iron is Fe. We know it has a +3 charge because of that Roman numeral that's present. Sulfide is sulfur on the periodic table, which is group number 6, and it has a -2 charge. Once again, if we just multiply those numbers together, that is 6. So we just need to get everybody to 6 to get to 0. So that means we need 1 more of the irons with a +3, and we would need 3 more of these guys there to do so. Gives us 1 and 2 of those. And 1, 2, and 3 of those, yeah. Any questions on how to write the names or do the formulas? And again, if it helps you to draw it out like I'm doing, why not do it? Yeah, you won't make a mistake probably, yeah. You don't have to do it that way, but if it helps you to do it that way, obviously. Any questions on type 2? So very similar to type 1. Only main difference is you need a Roman numeral to indicate the variable charge on the metal when you come across one. Any questions? So as we saw here, ones that are type 1 compounds that do not need Roman numerals are group 1, group 2, and group 3. Silver, lead, not lead, silver, zinc, or cadmium, which have fixed charges. Those that do need Roman numerals, again, are transition metals, and those guys just to the right below the staircase where lead and tin and all those guys are as well. All right, so I can't see it, but I think it's filled in on your notes. Is it filled in on your notes? I think, hopefully. That's like, they got like super small. I'm not even sure what it says, but I think it might be magnesium bromide on that first one, I think. So I think we got this. This would be obviously a type 1 because of the metal, right? So I think we added that to our previous one. So that is magnesium bromide. Not sure why I got super small on mine, but I think that is Li2O you have next, which is, again, metal, non-metal. So that's going to be lithium oxide. Again, group 1 has a fixed positive charge, so don't need any Roman numeral. Magnesium has a +2 charge. Group 2 does not need a Roman numeral. And the last one is that Cr, maybe? F2? So okay, thank you. CrF2 we'll go with. And chromium is a metal, but it is a transition metal, which means that we do need to figure out the charge on it. It's a type 2 compound. And we do know that F is group 7, which has a -1 charge, and there's 2 of them. So that gives us a -2, which would give us a +2 here. And that would be chromium, Roman numeral 2, and fluoride, right? And that, any questions on my extremely small ones? I'm not really sure what happened there, but super small. Right. So here's just a decision tree as to what to do depending on sort of the situation that occurs. Once again, type 1, type 2, they're both ionic compounds. They both have metals and nonmetals. And it's always, as I said, whenever that metal is involved, that is what you should focus on as to how you should go about naming it. And pretty much the only difference between these two is, do you need a Roman numeral or not? And it's, again, that's based really on the metal as to whether or not you need it. So type 3 is a little bit different, and it's actually, I think, pretty much the easiest of all of them, but it is the one that most people screw up on the most because they go, it can't be that easy, right? And so that. So type 3 is actually a covalent compound, and it's between 2 nonmetals. So in this case, we actually have sharing of electrons that are happening here. And your long-awaited wait is over. This is where we use prefixes. Yeah, this is actually the appropriate place to use prefixes, nowhere else. And we use prefixes like mono, which is 1, di, which is 2, tri, which is 3, tetra, which is 4. I think there's a table coming up there that has it on it. Penta, which is 5, hexa, which is 6, hepta, which is 7, octa, which is 8, nona, which is 9. Maybe I'm making this up. I don't know. Deca, which is 10, maybe along the way. Could be. So when we deal with type 3 compounds, pretty much we use the prefix and the whole name of the first element. And then we use the prefix, and the second name gets the nonmetal with the IDE at it, the end of it. Now, there are a couple of rules. First rule is we do not use mono on the first name, but it is okay on the second. So no mono on the first name, can use it on the second name. The other thing that very commonly happens is with the prefix and the first letter of the element, we get a couple of vowels that back up to each other. So very commonly we will get like an O and an O that sort of back up to each other on the name, or an A and an O. And typically the prefix O or the prefix A is sort of dropped from the name. So for example, if we take our good friends C and O, C is carbon, O is oxygen. Those are 2 nonmetals, which should make you really happy because frankly, there's nothing to figure out in terms of charges or balancing. You pretty much just need to write what's there. So I got how many carbons there? 1. Prefix for 1 is mono. Do I use it on the first name? I don't. So I'm just going to use the whole name in this case of it because I'm not going to use mono. So this would be carbon. How many oxygens do I have? 1. Prefix is mono. Can I use it on the second name? I can't, so that's okay. So I'm going to use mono, and then the second guy gets the IDE here. I now see what I was talking about there a second ago. I ended up with 2 oxygens that backed up to each other. So here we don't call it monoxide, right? We call it carbon monoxide, right? So we get rid of the first oxygen there, or O, I guess, and the proper name would be carbon monoxide, right? And that would be different than if I had CO2. C is carbon, which is a nonmetal. O is oxygen, which is a nonmetal. This should be called what? Carbon. And there is now 2 oxygens. This now will become carbon dioxide, yeah? What would N2O5 be? N is nitrogen, which is a nonmetal. O is oxygen, which is a nonmetal. There's how many nitrogens? Prefix for 2 is di, and the whole name of the first element, which would be dinitrogen. There's how many oxygens? Prefix for 5 is So here that would be pentaoxide, but we're going to drop the A because we don't get that A and O, and it will be oxide. Yeah. That is how quick you could do type 3. Nothing to balance, just pretty much pick what's there. The even faster thing that you could do is if you had to write the formula for a type 3. Let's say we wanted the formula for trioxygen. I just make something up, probably doesn't exist. Tetrabromide. First thing I should notice when I look at that is what's in those names. There's a lot of prefixes, right? Which tells me this is a type 3 compound. It is non-metal and non-metal action, and also tells me I don't have to worry about anything other than writing what it says. So tri is how many? Oxygen is O, so that's an O3, right? Tetra is, and bromide is Br4, yeah? Like you could do it in like a half a second, yeah? There's like nothing to figure out other than picking the right prefix and the right numbers based on these. These are the only places where you should use prefix in naming. It is only specifically for type 3 compounds where you have non-metal and non-metal together. Again, you shouldn't use it anywhere place. So those are really the two basic things that you should watch out for. Let's say I had, by the way, sulfur hexafluoride. What would be the formula for that? So sulfur with no prefix means how many? Yeah, just one, right? And that's because we don't use mono on the first name, right? But I do see a prefix on the second, right? So hexa is 6 and F is fluoride, so SF6, yeah? Everybody else, obviously, with ions, you do have to balance out the charges to 0.